Right. Hi, everyone. Welcome back to this section 7.3 video. And in this video, we're going to take a look at another example of inverse first translation theorem. And in this example, we're going to take a look at a common practice with these problems, which is completing the square. Okay, so let's check it out. So we have the inverse Laplace of s over 2 plus 5/3 over s squared plus 4s plus 6. So, we could try and factor, we can try to play around, but, one thing we could say is note, s squared plus 4s plus 6 is not factorable. Okay. Nor does it have any real roots. So the only thing we can do here is we must complete the square. Okay, so let's see how that works out. So completing the square, maybe recollect this at all from your K through 12 or some type of college algebra or above, but if not, it's okay. We're going to go over it right now. So we want to complete the square for this denominator, s squared plus 4s plus 6. Okay, so keep in mind that, this is in the form like ax squared plus bx plus c equals 0. Okay, so the first thing we want to do is move the constant c over to the right-hand side. So, we could say like move c to right-hand side. Okay, and then the next thing we're going to do is add a term to both sides. Excuse me, I wrote c here, it should be s. We're going to add a term to both sides, and what we're going to add is b over 2 squared to both sides. Okay, so this is part of the process of completing the square. So add b over 2 squared to both sides. Okay, so what I'm left with is s squared plus 4s plus 4 equals -6 plus 4. So this ends up being s squared plus 4s plus 4. Well, that factors cleanly into s plus 2 squared, and that equals -2. So we got the square. Okay, so let's bring that -2 on over. We have s plus 2 squared plus 2 equals 0. So that's our square. So, our original rational expression we are checking out turns into s over 2 plus 5/3. Now it was over s plus 2 squared plus 2. Okay, so this is our new inverse Laplace we need to do. Um, we need to get to that point, so we need to do a little bit of manipulation because we have like this s plus 2 in this denominator. We need to manipulate a little bit to get that s plus 2 in the numerator as well. So I'll make a note of that. Um, but we need to manipulate algebraically to get s plus 2 in the numerator. Okay, so I want an s plus 2 in the numerator. So here I have s over 2 plus 5/3 over s plus 2 squared plus 2. So I want to manipulate this algebraically. I'm a little limited. So one thing I'm going to do is add and subtract 1. Okay, it'll be the same thing either way because, what is 1 minus 1? Well, it's 0. So it's kind of like I'm adding 0 here. But we're going to manipulate it to work in our favor. So this would be going to move the positive 1 over to the left. So I'll have s over 2 plus 1 plus 5/3 minus 1, s plus 2 squared plus 2 on the bottom still. And I'm doing that because if I factor out a 1/2 of the first two terms, okay? If I factor out a 1/2 of the first two terms, what I end up with is 1/2 s plus 2, okay? And then 5/3 minus 1, that ends up just being 2/3. So I'm left with 1/2 s plus 2 plus 2/3 all over s plus 2 squared plus 2. Okay, so why am I trying to get s plus 2 in the numerator? Because I can see some type of like cosine or sine Laplace coming because I have this plus 2 down in the bottom. So I could kind of see that in the future because cosine and sine, what happens? Well, we have like plus something attached to like s squared. Okay, so that's why we're manipulating the top in case you were wondering. Because I can see in foresight that I'm going to need an s plus 2 on top. Okay, so this is our new term again, a new term. So we have the inverse Laplace of 1/2 s plus 2 plus 2/3 all over s plus 2 squared plus 2. Okay, so let's break this down. So what I want to do is separate this numerator out so I can have two separate terms. So what this would be is the inverse Laplace of 1/2 s plus 2 over s plus 2 squared plus 2 plus the inverse Laplace of 2/3 over the same thing, s plus 2 squared plus 2. So we're separating out the numerator. And one thing I also want to do here is take out the coefficients just to make it a little easier on us. So this will be 1/2 inverse Laplace s plus 2 over s plus 2 squared plus 2 plus 2/3 inverse Laplace 1 over s plus 2 squared plus 2. Okay, so I can already see like we were before, that I'm going to have some type of sine and cosine situation here. Okay, so I need to make sure my A's in the right formation and A squared is in the right formation and um, in order to inverse Laplace. So what I'm going to do here is change the numerator on that right term. So for this first one, there's really nothing I need to do. It's set up quite well for us. But this second term, I need it to be a little different in the numerator. So what I would need to do here is change that 1 to be square root of 2 over 2 over s plus 2 squared plus 2. Okay, and why am I doing that? Well, we'll get there in a second, but s plus 2 squared plus 2. I'm going to take out, excuse me, it should be square root of 2 over square root of 2. So this would be 2/3 times 1 over square root of 2. I'm taking out that 1 over root 2. Inverse Laplace, root 2 over s plus 2 squared plus 2. Okay, so now is where we apply that first translation inverse theorem. So recall that the inverse first translation theorem, f of s is shifting a units equals e to the at f of t. So my inverse Laplace of this term would be s over s squared plus 2 with s shifting 2 units to the right. Plus, this would be, I believe, 2 over 3 root 2 inverse Laplace of root 2 over s squared plus 2, and s is shifting 2 units to the right. Okay, so if any of that confuses you, we could break that down a little bit more as we are still learning this a bit. So, s plus 2 for this first term over s plus 2 squared plus 2. Well, what that is f of s, the Laplace transform, s over s squared plus 2 shifted 2 units to the left. I think I was saying right before, but it is actually left. So let me fix these because it's a positive 2, so we'll say plus 2. Apologies. Um, and 1 or root 2 over s plus 2 squared plus 2 is f of s equals root 2 over s squared plus 2 shifted 2 units also to the left. Okay, so I have s over s squared plus 2, root 2 over s squared plus 2. Maybe we could rewrite it a little more to make it easy for the transformation. So s over s squared. We could think about 2 as root 2 squared plus 2 over 3 root 2 inverse Laplace of root 2 over s squared plus root 2 squared. Okay, so why am I doing that? Because let's go to our table. Cosine and sine. Okay, so, you know, root 2 over s squared plus root 2 squared. Well, the inverse Laplace of that is just going to be sine root 2t. Okay, same thing for cosine. We would have s over s squared plus root 2 squared. Well, that's just going to be cosine of root 2t. So let's come back to the problem. And so what I would have here is 1/2 cosine of root 2t, like we said, but remember, we are also shifting. And so when that happens, we need to account for the exponent, e to the at, however many units you are shifting. So, this would be, a equals -2, a equals -2. So this would be 1/2 e to the -2t cosine of root 2t plus 2 over 3 2 over 3 root 2, also e to -2t. It's the same shift, sine of root 2t. And okay, so that is the answer. All right, so we did a couple things you might like, you might not like. Here, I was breaking it down as much as I possibly can. So we could see like all the intermediate steps and rewriting the equation over and over again. You may not like that. You may understand it already and just really go for it. So it's up to you, whatever you prefer. I just in this videos like to break it down, so that's why it seems very long. But if you understand the shifting and the notation, then you could definitely go for it. But that's how we do one of these problems, the inversing. And so we put together the first translation and the inverse translation and put it together for an initial value problem. But that's for another video. This one was just about inversing. But thank you for watching, and I'll see you in the next video. Okay, take care.